Let's start today with new module, and that is a Spark. So programming language is done. Scala, we know how to use it because without a Scala, we cannot understand even a single code in a Spark. So it's very important to know Scala first. Now, what is a Spark and how it is different from other programming modules? So MapReduce we have seen. MapReduce is one different type of programming module. I'll not say it's a programming language, okay? Because when I say programming language, we talk about Scala, Python, Java, R, OPS. These are all programming languages. Now, these are all APIs. So we'll be using this API to work with to work with Scala or Java or R or Python. So we'll see how many languages uh, Spark supports and how it is different from MapReduce. We'll go first to history of a Spark and how many components we have. Okay, it's a very important tool today. It's like one alternate for Hadoop interface. So wherever we used to have MapReduce or other business before 2015, mainly it was in Hadoop 2.0 architecture. So everything has moved on to Spark architecture. Okay. Spark is very important today. If you just search for data engineer openings, you'll find everybody is asking for a Spark. Okay, so extremely important topic. If I say after MapReduce, this would be the important one because otherwise, so far we have seen tools Hive, Scope, HBase, right? So those tool we can quickly learn in maybe 2 or 3 days. That does not take time much. This will take some time to understand. And obviously, because this is conceptually, you're not using any tool, you are writing your own concept. Spark earlier name was Sark, and this came in picture. So why we started working with the Spark? Because MapReduce have several limitations. We'll talk about limitations. This came in picture after 2006, okay, and 2010. Actually, we started getting the stable releases. 2012 was the first year when we get the release of Spark, which was stable. So first release of Spark was 1.6.0. That was the version. Nowadays, we are working with 3.x of Spark. So this is having third generation, same as Hadoop. Okay. Spark founder is Mati Jairia. Spark founder is Mati Jairia. This project is started actually with the MPLAB in UC Berkeley, US, and later it was acquired by Apache Foundation and Databricks. So Databricks on today, this is Spark, and Apache Software Foundation company are putting their several contributions to increase the version, increase the features, and obviously their speed, their lightweight, and many other features. So how is Spark is different from MapReduce? That's very important question to know. So one side will write MapReduce and one side will write Spark. I cannot say it's a replacement of MapReduce. That won't be a fair statement because MapReduce has its own use case and Spark has its own use case. Okay, so MapReduce is there since 2008. We get this version in 2008. We get a stable release after 2010 for Spark, and that was 2.6.0. So let's do benchmarking first for MapReduce and Spark. MapReduce can only deal with, okay, can only deal with batch data. Can only deal with batch data. When I say batch data, it's a historical information, right? Some data is already available and you are storing that data to HDFS first, and then you're writing MapReduce program using Java or Scala. This two option is available most widely. So when I say historical or batch data, can we see the flow? Now, all the time we are extracting data from our downstream sources. So flow goes on this way. You have upstream source. We used to refer this upstream source as our web server from where we are getting the data. Let's say this is some kind of website, okay, or maybe a flag file locations. Then we get this data to downstream source, which is nothing but our RDBMS. So data is keep committing in this location. This is your relational database management system. It can be anything, okay? Oracle, MySQL, PostgreSQL. I'm talking about currently the typical flow where we need a MapReduce. Now we are extracting this data to HDFS, which is our centralized repository. There are many names for HDFS. We call it's a staging layer. We call it's a data lake. So depends. Now data stream source will extract. So for this purpose, we have seen our scoop utility, which provides us ETL job, extract all this data, and then on this HDFS dataset, and not just Scoop can do, actually Spark can also do, Spark SQL can also extract data, but Spark SQL does not have few properties, like it cannot take any inserted data, updated data. For that, I have to design my own program. There is no defined utility unlike Scoop. But in Scoop, it's already there how you can get inserted data. So we just pass incremental append, incremental last modified. So data is extracted. I can do the same using Spark SQL here, get this data from this source to destination, but I will have to write my own job. We'll see that in Spark SQL, how to handle this part. Now data is present, I'm assuming, because without data present in HDFS, I cannot write any MapReduce job. Now on top of this, I'm writing one MR model. Okay, I'm writing one MR model as in, because MapReduce is a programming model, right? So I'm writing my code in MapReduce to handle this data based on the applications, whatever business is asking. Let's say business says I want last 10 years data, I want use cases can be this. What you write in MapReduce module, I should say this is a module. What we write in this MapReduce module depends on the application or the problem statement. You are taking this data from banking or telecom or logistic or e-commerce or media services, which business you are with. Okay. If it is a healthcare business, we say we only want to process the data people who are diabetic. Let's say I'm saying I want to see the data who are diabetic, so filter this data only. Then I'll say people who are having hypertension, I want to see this information, I want to process this data. So here in this diabetic also, I want to take the category like pre-diabetic, diabetic, acute diabetic, and based on that I want to do analysis. Then I'll take this data to Hive, and at last this is going to the highest layer, which is the data science layer. So we are using this for predictive analysis. Then hypertension, this is related to say healthcare industry. Suppose I'm building a use case for banking. Okay, so I'm not saying this is the best or this is the best. You cannot justify your favoritism here. We should say favorite based on the problem statement always, because we never know this can come or need what time. This when we need a Spark. So to understand when we need MapReduce and Spark, we need to know there all the features first. In banking, so let me write here. This is from healthcare industry, and this is from banking industry. In banking, I can extract data and start analyzing people who are people who are spending. So from any bank, okay, this can be people who invest more than 30,000 using credit card. I need this data set from this, because all the data is already extracted in HDFS. So I'm writing one program in MapReduce and analyzing this data. So this is like a transformation you're doing, okay? Transformation or data pre-processing you're doing. Then second would be you again want to filter people who were spending more than 50,000. So you're kind of creating a different groups so that you can send them a promotional offers, right? If this guy is there, this is a premium user, I can maybe give him a domestic uh, domestic flight a launch access. This can get some uh, discount on any product purchase on Amazon.com, like that. Third, maybe I'm saying I need people who have opened their account in last 5 years. Okay, so these are all your use cases. These are coming from business. Business will tell you we need this data. You'll have to write a program and give this data to them. Ultimately, you are processing this data and then you are storing this data to Hive warehouse so that you can run a query and Hive data can be accessed from other services. Spark can also handle the Hive data set, and I have used mostly Hive warehouse as my source for data science, because ultimately the funnel flow reach to data science for sentimental or predictive analysis. So hopefully this is clear. We can only work with the historical data, not a real-time data. Whatever data is stored already in HDFS, Spark earlier it was not supporting it was not supporting more on the batch side, but nowadays, okay, the latest version of Spark which we work, it can handle batch data definitely, and it can handle real-time data as well. So I should not say 100% real time, because nothing is 100% real time. So we always call it's a near real time. Okay, because if it is traveling through light speed also, 80% data can be real. Now, this is a benefit, right? Because this real-time data cannot be processed using MapReduce. Now, MapReduce is developed in 2008, stable release, which was 0.19 version. You can Google it up and check in the Apache Foundation site, because everything is open source. This is also open source. This is also open source. Whatever we learn in Hadoop, everything is open source. Spark stable release, I'll say this we get in 2010. Okay. Their benchmarking. So MapReduce benchmarking is they can process they can process 1 terabyte of data in 60 seconds. So let me write the time first. They take total time 60 seconds to process 1 terabyte of data, 1 terabyte of data. But using how many machine, how many node, what is the cluster size? This cluster size is 910. This is their benchmarking. They tested it, and in 2008, by the way, MapReduce was the winner for processing high volume of data. If you go 12 years ago, there was no such tool defined to handle this large volume. So it was extremely fast by the time. We are 12 years ahead already from this year. So this is taking the same time, 60 seconds, and processing roughly 4.27 terabytes of data, okay, every minute, using how many machine? 209 machine. So in textbook, in literatures, in top-notch forms, we write that Spark is 100x faster than MapReduce. But question is not faster. Question is how and why it is faster. What algorithm we are using in Spark, that's why it is behaving much faster than MapReduce. So that concept is based on one single release of Spark, that is it is an in-memory processing model, and this is a disk computation. MapReduce is a disk computation. Again, I'll design a flow of this MapReduce just to revise so that we can compare it better. Okay. Disk computation, when I say my data is stored in hard disk, my data is stored in hard drive, and then I am reading from hard drive and processing it. We know that MapReduce is a two phase, right? Map phase and reduce phase. map phase will give us key and value, and reduce phase will aggregate that. It can handle also any type of data, but only problem with it cannot have this near real-time data activities inside MapReduce. Now let's go and see this disk computation model. So I'm assuming my data is already present in HDFS. Okay, this extraction is already done like a scoop. And now I have built a MapReduce program using IntelliJ. I have created a jar file. I copied that jar file to my Hadoop server where my Hadoop is already installed. So this is your step to do. First number, we create a first step, we copy the data or we extract data to HDFS. We extract data. This is what we should write once our everything is done when we do project part. So what you are writing in roles and responsibilities, that's important because question will come from there only. We extract data from source to HDFS using ETL. I'll not specify Spark SQL or Informatica or Scoop. I'll just say ETL. Okay. Second, once data is present, create a jar file. Create a jar file using some IDE. That can be Eclipse SDE or that can be IntelliJ IDE also. So what is the flow? Create a jar file following below steps. So first step for creating a jar file, we open an IntelliJ. I'll say IDE. This ID can be Eclipse or IntelliJ. When I open this, this is in my local machine. I'm doing it. Then I create a project. Then I create a package. Then I create a class. I write a business logic there. After creating a class and writing business logic, I will test it. Testing means I'll compile it. Whether it is taking care of all the functions, is it processing all the data which is asked by business, everything is good. Once I am sure that all the data is processed and functions is working, uh, here I'm writing two things, okay, main and test. In main, I'm writing my main functions, my main classes. In test classes, I'm writing the test functions. I'm writing the test courages. After compilation, I will create a bytecode, and this bytecode is our jar file, Java archival, because your Scala is also built on top of Java. So we can say it's one wrapper class of Java. So that's the reason whatever you are writing in Scala will work in Java also. But whatever you're writing in Java will work in Scala. But what you're writing in Scala, it needs a Scala plugin. So without a Scala plugin, you cannot use it. After creating the bytecode, this is nothing but a jar file. I will copy this to Hadoop server. And we have seen Hadoop server when we say, are we creating a manual server or are we using any distribution? Always for production, you use any distribution services such as Cloudera, CDH. I think the latest release is somewhere in 6.0.2 of this Cloudera. Then there are Hortonworks also, which are by the way same company today. Hortonworks, Cloudera. Mapr is there, acquired by HP. Then I have a cloud computing platform. I can use Amazon Web Services, I can use GCP, I can use Microsoft Azure, like this. So AWS gives me one, same as CDH, AWS gives me one ready-made service for Hadoop, and that service name is EMR, Elastic Map Reduce. Using this EMR, whatever I'm doing in Cloudera, I can do that also. But unfortunately, if you want to test it, this is not free. You'll have to pay some bucks for this. GCP is free, so you can create a data proc. I think we have seen creating a data proc cluster, which provides us everything ready-made. Azure is also there, so let's not talk about Azure. This is what I'm doing in typical MapReduce flow. Now, after doing this, third step is After doing this, third step is I will submit my jar file in Hadoop server. Now let's say this is my Cloudera, because we have seen extensively this Cloudera. I'll open my terminal and write the below command. So open a terminal and write a below command. You will be writing here Hadoop jar. Then when you create a jar file, this will have some name. Let's say that name is test.jar. Always that will have extension as .jar. So test.jar, and after test.jar you will define your class name, package name, and class name. So we'll write here package name dot class name, package name and class name of your project. So package and class name, because if there is no package, just a class name. After package and class, we will provide our input location, and input from where. This input data is already present in HDFS, so we will provide location of HDFS, and this data will be processed using this business logic. Whatever output is generated, this will store in output underscore HDFS. This will take some time, and this I'm doing for one job. Now, if you ask me how can I handle the 10 jobs, we'll see the scheduler part for that. Okay, Uzi, Tivoli workstation are there, which are a coming topic. If I want to submit 10 jobs at a time, then we need a scheduler. We cannot do terminal wise one by one. Terminal is only for one job at a time. Output underscore HDFS. This will take, let's say, 1 hour time, read the input data and give me output data based on this business logic, which you have written in your program. After you get the data, this data we know how to manage it. This is about your MapReduce flow. But where disk computation is coming, we are seeing all these steps because to understand this disk computation model. So disk computation is this MapReduce flow. We already seen this, but just I'm recapping things. MR flow, you have input data available. This is already in HDFS. I'm talking about this data, by the way, this input data. This is already present in HDFS. After that, we have input split. We split this data, which is a logical is split. Logical division. This is a physical. This is a logical division. Now, from input split, all this process start happening inside my mapper. So after input split, then record reader will be there. Record reader will read records one by one. Then it will provide to mapper. It will work with mapper face. It will take every key, individual key, provide them a value. And then after mapper, if we need a combiner to perform a disk level aggregation in a local machine. So we use combiner, then after combiner, we use partitioner to send our key. And after partitioner, we go to shuffling sorting, shuffle and sort. This is a part of wherever I start combiner, after combiner, it's a reducer stage. Then after shuffling and sorting, we do reducer, right? Before reducer, it's a record writer. So most of the textbook does not have this record writer. You'll find in this in the literatures, okay, in top-notch firms or universities. After record writer, this is going to reducer. And after reducer, the final output goes to your output directory. Now this output directory is HDFS. So input and output is present in HDFS, but this flow is happening inside your node manager and resource manager with the flow of it. I think so. Swapnil, you may check. Rutikesh, Are you able to not hear me? Satish? Okay, maybe network issue. So input, output is in HDFS, and these are a process which are happening inside. Okay, and when I say inside, this is all step is happening in your node manager. Node manager is our slave services. Resource manager and node manager are there. Resource manager are communicating to node manager. Node manager are transferring back information to resource manager. Now, the main problem, which is, I cannot say problem, but why your MapReduce is slow? Because of this internal operations. Whatever output is processed, here we have two phase, right? One phase is mapper phase. This is a first phase. This is your second phase. Whatever you do in mapper, this output is input for this reducer, which starts from here. Now the question is, if I'm writing mapper output in disk, whatever mapper output is there, I will be writing that output to disk, my hard disk. Okay. So when we call this as an intermediate location. Okay, intermediate location is terminology, but ultimately it goes to disk only, local disk. So reducer will read this data from disk and then process it. So reading from disk and reading from memory, which we'll see in Spark, memory is anytime faster because we cache the data. Okay, we will cache the information. So if I compare, this difference is coming because of that service only. The big difference 1 TB and 4.27 terabyte. Though here I need more number of machine, which is 910, and here I need just 209 because this is a in-memory processing model. Spark is a in-memory processing. When I say in-memory processing, is it strictly in-memory processing or it's up to me? So I can choose it. If I want to work with the in-memory, I can do that. If I want to work with a disk, I can do that also. So I have an option for cache and persistent. Okay, it's not telling me that you have only one option to work with and that's in memory, because if a Spark gives me only one option, I will tell you the challenge. I can only work with the data when I have good RAM. If my system RAM is 2 GB, 3 GB, I cannot deal with large volume of data. Okay, so here we need to know what is our cluster capacity in terms of RAM and CPU. Since option is with me, no need to worry. If my memory is less and I'm processing with historical data, huge historical data, I can still do the disk operation. I will write my code in Scala. I will use API of Spark and handle this using in-memory computation. So that's one difference between your MR programming model and Spark model. Never say these are language. They are APIs designed to work with a programming language. Now, MapReduce is fitting. MapReduce is fitting with Java. So Java is a native language for MapReduce. Java and C it uses. So I can do that thing in Scala also. I can work with Python also. I can work with Ruby, Groovy. There are many languages. Anytime if you see you're learning any module, any module or any model, and you see that the native language for that model is designed in any of these languages. Fortunately for MR, this is Java and C. So it will give you best fitting with this programming languages. When I say best fit, uh, they support large number of APIs for these languages. Maybe I can see some issues, and I have personally faced writing a Scala program for MapReduce using a scalding framework. So sometime it is not able to give the latest API somewhere. We are getting computations issues. So issues are there. But in a Spark says you can work with Scala. Now I'm writing Scala for a reason first, because Spark is built on language of Scala. So this is the reason Scala being popular after 2010, just because of Spark. However, I can do in Java also. So it provides the support for Java. It says you can use a Python also. You can use R language also, and you can use SQL interface also to write your query. All 5 languages we can work with. Okay, so this is the difference between your two programming models. Now we'll go and see Spark components. MapReduce comparison is over. If somebody asks you, because this would be the first question, why you want to work with Spark, why not MapReduce? So we should know, and we should be good with the differentiations. With all other tools, like somebody asks you, what is the difference between Hive and Scoop? We should be able to tell that also. Spark components, just like in MapReduce, in Hadoop we have a component MapReduce and HDFS. HDFS is for storage and MapReduce is for processing. Spark has also their components, or I can say Spark modules. Spark modules. The first module is a Spark core. This is like your main processor, scheduler, main. This is the heart of Spark. Okay, so Spark core, all the scheduler, job activity, CPU computation, RAM, everything we are defining in this core. So this core will be somewhere here. Let's say this is my Spark core. Okay, this is my Spark core. And top of this is Spark core, because if I want to work with a Spark streaming, Spark SQL, Spark graphics, Spark machine learning library, whatever modules I have, I need to first take this Spark core, which we call a Spark using a Spark context. We'll see that in program when we go. So Spark core will be your base layer always. Just like you keep the data to HDFS, Spark core is for schedulers. Okay, scheduling, providing resources to your other modules. Then after Spark core, it is a Spark SQL, and Spark, using a Spark core, I can handle my batch data. So let me write it. This is specified for batch or historical data. It cannot deal with the real-time data. This utility or this module cannot handle the real-time information. We have a separate module for real-time. I'll come there in a while. Spark SQL. So as the name suggests you, SQL, this is defined for data sets or data frame, I can say. Okay, there's a difference between data set and data frame. You'll see that based on the version we call data sets and data frame. So a Spark SQL can handle directly your RDBMS data in a tabular format. That's a good use case. Second, I can directly process my file. So write it here, directly I can process a file, which are JSON data, which are Parquet data, which are for CSV. I need to write my own one plugin, but I can handle this also. I can handle I think Avro. Avro also start supporting, so we can handle Avro also. We are running query on RDBMS data. We're extracting data from RDBMS, and we are accessing our Hive table also. I think there is one plugin defined. Using that, we can access our H-based data also. Okay, so in Hive, I can do all the operation. The best part is I can do DDL, DML, DRL. Now, since I'm able to do DDL, DML, DRL, why do I need Impala? Okay, so due to this Spark utility, Impala we have seen after Hive, right? How things can be faster in Impala. It's a module. It's one utility which will provide you in-memory processing. So there are two options. In Hive, you can change the execution engine, or in a Spark. So in GCP, we have seen this Hive execution engine already. This Hive execution engine is TEZ in GCP. They have set it by default. But in Cloudera, this execution engine was MapReduce. So whenever I'm running a query, it takes time because of MapReduce. It's a low-level programming model. We call MapReduce as a low-level programming model, and Spark as a high-level programming model. So Spark SQL utility, third utility is for define real-time data sets. So Spark streaming, as the name suggests, is streaming, right? So here we can define our window interval. I can I can micromanage my data of 10 second, 20 second, 30 seconds. I can define the window width. Uh, Spark streaming, this is for real time, which we often refer as near real time. 80% data typically is 100%, typically is real. So near real time data, we need a good memory. You cannot work with less memory if you want to work with a Spark streaming. You need a good amount of RAM here, okay? Because you're not saying that this data is stored somewhere and then you're processing. You need to have interactive operations with the Spark streaming. So they are known as a memory hunger. We'll see why they need more memory when we start talking about the Spark streaming separately. So being a data engineer, I should know this three part first. Okay, once I am good with this three part, fourth and fifth is not having much use cases. Fifth is just defined. This is for data science, data scientist people. Fourth, however, I'm using it some places. So this is known as a Spark graphics. Fourth one is a Spark graphics. Graphics means here social media uses this in organizations also we can use just to get a connection, right, between 1 to 2 seconds. So example wise, if I take graphics, we have three, we are, let's say, four people, and we see that this is A, this is B, this is C, this is D. So this guy know this guy, this guy know this guy, this guy know this guy also know this guy. So all their friend, ABCD are friend, and this I'm talking about a Facebook connections, let's say. Now Facebook wants to recommend something for D. So Facebook uses this kind of operations, graphics, where we have two things, vertex and edges. Okay, so we call these are known as vertexes. These are known as a vertex, and this line, this straight line, this parallel line you see, as a edges. Okay, so when I want to recommend something for this guy out of ABC, so A and B and C is already known to each other, but D is only friend of B. So now this A and C both will be recommended for D because B knows both of them. So this is how they work. They use some other parameter based on the location, based on the same organizations. So they have a priority. If they are coming from same organizations, we should define them first, then second. So priority we'll see. Uh, in Spark graphics, it is working with your uh, relational connections, I can say, not a relational data. It provides you relations between one node to second nodes. Then fifth module, earlier in Hadoop early days, there was one service named Mahout. So I don't know if you have heard it. Mahout is one which was providing us machine learning operations. Okay, artificial intelligence, deep learning. You must be listening today. So artificial intelligence and machine learning, deep learning, they're popular after 2012. So Mahout was there to handle this, but Spark said we have defined machine learning library. So it is known as a ML library, machine learning library, which can perform hypothesis testing. It can have all dimensionality reduction, principal component analysis. So mainly for people who are into data science field, not for data engineers. So this is for data science field. This is more important. After this three, you can give a priority to this, and you can see one or two program for this also. But 95% time we'll have to invest in this three things: core, SQL, and streaming. Now Spark core is there where other things are fitting. So if this is a Spark core, if this component is Spark core, so other services I have top of this. Other services are there top of this, which are Spark SQL, then Spark streaming, Spark graphics, and Spark machine learning library. Spark machine learning library. Now they uses Spark core for their scheduling options, how many CPUs required, how they're computing things. Okay. Now after getting this 5 points, Spark can work with which environment? Okay. We have seen where Spark is fitting in our HDFS picture. So if I define a Hadoop flow, there is a HDFS, right? We say this is our centralized uh, repository and often referred as a storage layer. This layer is known as a storage layer. Then we have here computation layer, which can be yarn or mesos. So here I will write yarn and mesos. Yarn and mesos is my computation layer. Both are from Apache. We have seen the yarn computation. Some uses mesos also. Computation layer. Then we have application layer, and that application layer is MapReduce, PEZ, and Spark. So Spark is fitting. I'm not specifying Spark core or SQL. I'm only writing Spark, which means all the module of Spark. Okay. So this is the flow of your uh, program or writing process. This is your application layer. Now, whatever you write in Spark using any module, it goes to yarn, and then yarn is computing. It is reading data from HDFS. Now, does that mean to work with Hadoop, to work with Spark, I should know Hadoop first? That's one requirement. Yes, if you want to work with the Spark, you should know HDFS. Not just HDFS, you should know basic concept of Hadoop. But if you don't know basic concept of Hadoop, Spark provides you multiple storage options. You can store in HDFS. That's one. So prerequisite. Here I will define this as a prerequisite. What are the informations I need first? Here I'll say I need the basic operations of Hadoop, especially HDFS, because Spark is using HDFS for storage. So this is not the one option only. Spark uses HDFS only for distributed computing. When I want to handle the large amount of data, I can store it. But what if it is handling real-time data? Because real-time data cannot be stored in HDFS, right? We'll see that. First is a prerequisite of Hadoop, and second, I should know Scala to write a program, Scala or Python, any one of them. Because Java we cannot. Java is as similar as a Scala. Third point is it can store. So this is your prerequisite. There's two things we should know before starting it. I think we are good with this, both the point. We know Hadoop also, and we know Scala also. Now, where they can store their input. So Spark can work with when I say can work with, which means where they can store their input. So first, obviously HDFS. If large volume is there, if I'm testing it, okay, currently since we are beginning this as Spark, so we cannot directly go to HDFS and see it. So we can use a standalone operation also to store data. Standalone. Okay, standalone means there is no Hadoop services running. Third option is after HDFS and standalone, I can store this to Amazon Web Services S3. So Amazon Web Services is a platform where we compute our data set. This is a cloud computing, and S3 is a storage service. S3 is like a bucket where we store the data. Simple storage service. That's the full form of S3. Okay, so this is the third option. Now we will see basic standalone first, then we will go to HDFS. how this two can be managed. Then Spark can work with these three things. After that, let's start the architecture of a Spark now. Since we know how it is different from MapReduce, so we can compare it why we need to work with a Spark. We know how many modules are there in Spark. How to create a Spark jar, the flow will be same as this MapReduce. I'm not doing any extra thing. I'll open my IDE, which is IntelliJ. I will create a project. This project will be a Scala project using SBT, and then I will write a class using a Spark module. So I need to write the dependencies here. I need to download my dependencies from where? From Maven. So in Maven, I'll get the SBT dependencies, and then I can compile it. I'll create a bytecode, and submission process will be different. So in Hadoop, we are using Hadoop jar. In Spark, there is an option for Spark submit. We'll see when we create a jar file and move it to Cloudera. Now, what is the architecture? What is the architecture of Spark? Okay. Now, before going to architecture, in which method? So, because architecture will take time to define, since we have less time, let me take another point. Spark works with below execution model. First one, they use the scheduler called DAG scheduler. Now, DAG stands for directed acyclic graph. Directed acyclic graph. So there are two different types of schedulers. One is a DAG, second is a DCG. DAG is a directed acyclic graph. DCG will be directed cyclic graph. When I say acyclic graph, so whatever I have done in this step, let's say this is my step number A, I'm processing something here. Let's say here I'm processing one data related to diabetic people. Then second time, if I'm again trying to write some use cases of this A, so I'm not again processing in this B. What I can do, I can directly read it from this A point. So A is processed, acyclic means it goes to this point. Here I'm processing something, and if this B needs to process some data which A has already processed. Remember, there are 2 points. First point, A has processed some bit of data, okay, based on some cases. Now B also want to process those data which A has already processed. So B will not start it from again, which your MapReduce does. MapReduce always do read from HDF, we read from disk and process it. We are saying this is an in-memory and DAG operation. So B can directly read from the cache. Whatever A is doing, if it is in-memory operations, this A is caching that. A uses the cache operations. So B can directly read from cache, no need to repeat it. Then if I'm going second to this point, which is C, suppose here I want some input from again A. Okay, I need some input from again A. So C can also read from A, or C can read from B also. Whatever I'm processing, I'm just keeping this information in a cache. If I'm doing something on D now, again, this data is caching. And the best part I can decide actually, I want to cache this. This is up to me. It's not by default caching it. If I think I should cache this, I should not cache this. I should cache this. I should not cache this. So anything you can define it based on the operations. If it is, you need that output every now and then, you can cache it. If you don't need them, you cannot cache it. So customization is available. That process we'll see when we will discuss about cache and persistence. There's a separate concept in Spark code called as a Spark cache and Spark persistent. So this process I'm calling as a directed acyclic graph. Acyclic, you say, when they are not going from this is a cycle. If I communicate from A to B, then B to A again, this is a cycle. Okay, but this cycle I'm not doing it. I'm directly reading from cache. Hence we call it's a directed acyclic graph. Second will be our RDD. Second will be using extremely is the RDD. Okay, so all the heavy lifting of our programs or of our data set will be taken care by this RDD. What is the full form of this RDD? RDD stand for resilient, resilient distributed distributed data sets. Every word has a meaning here. Okay, resilient distributed data sets. So resilient is actually coming from Oxford, like basic general English. We call resiliency. So from resiliency, there is a resilient. Now, what is the meaning of resilient? If you are crashing something while processing, your some data is not processed 100%, and in between they failed. We have seen that in MapReduce. I am having task issues. My task is failing in between, or my node is failing in between. So what we do, we notify to resource manager. Then resource manager will find out a new node to submit this task. But the problem was this task is starting from 0%. That was the problem. If it is running in other machine, resiliency means they try and try. So if I correctly remember, the minimum time is 16 times they try. This is based of my knowledge. So 16 times they retry. If this is failing, they continue try in same node, in other node. If still this is not working, then they will give you issues. So resiliency means the person who never give up. That's what we call a resilient person. So resilient means somebody never gives up. Example wise, you can take a kid is running, falling, again stepping, again running, again running. That's what is a resilient kid. Distributed, I am saying if I want to divide my data, and this distribution is coming because of Hadoop distributed file system. Hadoop distributed file system. In HDFS, you will find D stand for distributed, right? So what we are doing, we are storing our data in 128 MB of block size. This is what is our distribution, 128 MB of block size, which is a by default size. We can increase and decrease this. Customize option is available using the FAQ, that was dfs.block.size. So if you need this, you can do. Otherwise, by default, it will use this distribution. And this is why we should know this point to work with HDFS. So Spark can handle this. Dataset is your form of data. So whatever data is present in this 128 MB, that's what I'm calling as a data set. Now, whatever data your MapReduce can process, structure, unstructured, semi-structure, everything can be taken care by Spark. So architecture part will start tomorrow to discuss with other components of Spark.